These notes are over the transfer of thermal energy. So each substance has a physical property that's known as the specific heat capacity. So specific heat capacity is just the amount of energy required in order to raise 1 kilogram of whatever the substance is by 1 degree Celsius. Okay, and so Celsius and Kelvin, they both increase at the same rate, so we can use either one. They just have different set zeros. Okay, so 0 Kelvin is equal to negative 273.15 degrees Celsius. And so if we're converting from Celsius to Kelvin, we'll just add the 273.15. If we're going from Kelvin to Celsius, we're going to subtract. Okay, so I'll have the answers up here on these. So if we were considering the specific heat of a sample of aluminum, okay, the heat capacity is 800 joules per kilogram degrees Celsius. So if we look at this first one, it has 800 joules, which we know is the required amount to raise 1 kilogram 1 degree. So since we have 1 kilogram, we know that the change in temperature is going to be 1 degree Celsius. Okay, for the next one, we have 1600, which is double the amount for 1 kilogram to raise 1 degree Celsius. So this is going to be a change of 2 degrees Celsius. Okay, for the next one, we have 4 degrees in temperature change. So 4 times by 800 joules per kilogram degrees Celsius would be 3200. Okay, and so we know that this is 1 kilogram because it has the amount of joules we need to change 4 degrees for 1 kilogram sample. Okay, the next one has an 8 degree change. So 8 times my 800, that would give me 6400. So we know again this is a 1 kilogram because the energy input is 6400. All right, for the next one, we have a 2 degree change. So 2 times my 800 would give me 1600, but you'll see that it's a 2 kilogram sample. So we're going to have to multiply it by 2 so that we get 3200 joules required. All right, and then for the last one, it's a 4 degree change. So 4 times my 800 would give me 3200, but it's half of the sample. So half of 3200 would be 1600 joules. All right, so here's the equation that we're going to be utilizing in order to find the change in thermal energy. So we have mass times C, which is the specific heat, times the change in temperature. Remember that change in temperature is going to be our final temperature minus our initial temperature. All right, so for example number 1, how much thermal energy needs to be added to 1 kilogram water to heat it from 200 degrees Celsius to 92 degrees Celsius? And it tells us the specific capacity, heat capacity of water is 4,186 joules per kilogram degrees Celsius. Okay, so the equation that we're using is the one above. Okay, one thing to note too, our mass needs to be in kilograms, which this one is given in kilograms. So 1 times our specific heat times our change in temperature. So our final was 92 degrees minus 22, which is our initial. So then whenever we multiply that out, we get that our thermal energy change is 293,020. So here's a chart of specific heat capacity values of common substances, and I just want to take a second to just kind of look at the two different sides. So we have the this side that has lower specific heat values, and then this one has higher specific heat values. So this side requires more energy input in order for the change in temperature of 1 kilogram of a sample, whereas this one does not take as much heat or energy input in order to change the temperature of the substance. Okay, and so what we should notice is that these that have very low specific heats are things like metals, So our metals have low specific heat, okay, and this is because they are good conductors. Right, so that specific property makes them good conductors is the fact that they have a low specific heat capacity. Okay, one other thing to note here, these first three that they list, we have water, ice, and steam, all three of which are made up of H2O. Okay, but you'll notice that the liquid state of H2O has a much higher, almost double the CP, or the specific heat of the solid or gas form of water, of H2O, okay? And so this just has to do with the way that liquid H2O molecules interact with each other. They like form hydrogen bonds and things like that. Whereas in the ice structure, they produce more of the crystal-like structure. So they're not interacting in the same way, and same with steam. They're not close enough to interact, which doesn't require as much energy to raise the temperature compared to the water, the liquid water. So we've been talking about the law of conservation of energy, and so in a closed system, if we had hot water in a kettle, as the water in the kettle cools down, what happens is the energy is absorbed by other objects around them, okay? So the thermal energy is conserved in that the kettle, the countertop, and the air around the room is going to heat up due to this flow of thermal energy. Okay, and one thing to note is that thermal energy is always going to flow from high to low, so from high temperatures to lower temperatures, okay? It doesn't flow in the opposite direction. So mathematically, we can state that if we have two different substances where one is at a higher temperature and one is at a lower temperature, the change in thermal energy of the absorbed substance is equal to negative the change in thermal energy of the released substance, okay, or the substance that's releasing the thermal energy. Okay, and just to note, this is negative because whenever we look at the released energy, it's actually getting cooler. So it's final temperature minus initial temperature. This is going to be less, and this one is actually going to be greater, okay, because it's actually cooling off as it goes through. Okay, so we can expand out these equations so that we have the mass of 1, specific heat of 1, and then change in temperature of the absorbed substance is equal to negative the mass of the second substance, the specific heat of the second substance, and then the temperature change for the substance that's releasing the energy. So for example number 2, an 18.3 gram sample of an unknown metal is heated to 238 degrees Celsius, then placed on a calometer containing 500 grams of water at 18.20 degrees Celsius. The final temperature of both the metal sample and the water is 18.45 degrees Celsius. Determine the specific heat capacity of the metal and identify it using our table previously in our notes. Okay, so I'm going to start by just writing out the information that we do know. So for water, they gave us the mass. They did give it to us in grams, so we have to convert it to kilograms. So we have 0.5 kilograms of water. The specific heat of water, we can go back and look at the chart given above, and it is 4,186 joules per kilogram degrees Celsius. And then the initial temperature it gave us was 18.2 degrees Celsius, and the final temperature is 18.45 degrees Celsius. Okay, so those are all the variables for water. And then so next I'm going to look at the unknown metal. The mass they gave us in grams, I have to convert it, so 0.183 kilograms. The specific heat, we do not know. That's what we're going to be trying to calculate. They did give us the initial temperature of 238 degrees Celsius, and the final temperature is going to be the same as the water, so 18.45 degrees Celsius. Okay, so remember that for the equation, we have a change in thermal energy of the absorbed substance is equal to negative the thermal energy change of the releasing substance. Okay, so we have to determine which one is releasing energy and which one is absorbing energy. So the one that is releasing is going to be getting colder, okay, or the temperature is going to drop. The one absorbing is going to be getting warmer. Okay, or the temperature is increasing. So if we look, the water went from 18.2 to 18.45, so it does increase, whereas with the metal, it started at 238 and it dropped to 18.45. Okay, so this is going to be our releasing energy. This one is our absorbing. Right, so now we can plug in the information that we know. Okay, so the mass of my absorbing substance was 0.5. The specific heat was 4186. My final temperature was 18.45 minus my initial 18.2. It's equal to negative the mass of my releasing substance, so 0.0183 times the specific heat, which that's what we're trying to find, times final temperature minus initial. Okay, so whenever I multiply it all through, get C all by itself, I'll find that the specific heat of the metal is 130.23 joules per kilogram degrees Celsius. Okay, so if I look back at the chart, it's going to most closely match gold as the unknown metal. Okay, I'm going to skip this part just because what it does is it expands out the previous equation that we just used, but I think it kind of just makes it more confusing to know which equation to use. Either one works for the problem, so I think just sticking with the one is more simplified, but I do want to just make a note, because you will need to know this, is 1 liter of water is equal to 1 kilogram of water. Okay, so that'll be important whenever you need to convert between liters and kilograms. For example number 3, it says, what is the new temperature of liquid if we have 0.75 kilograms of a liquid at 35 degrees Celsius and it's added to 0.25 kilograms of the same liquid at 60 degrees Celsius. Okay, so the first thing I'm going to do is I'm just going to label. This one is going to be liquid number 1. This one is going to be liquid number 2, just so I can keep them separate. So if I list out my variables that I know, the mass of the first one, they gave it to us in kilograms, is 0.75 kilograms. Okay, we don't know the specific heat. We do know the initial temperature is 35 degrees Celsius, and we don't know the final temperature. All right, for substance number 2, the mass given was 0.25 kilograms. We don't know the specific heat. They did give us the initial temperature of 60 degrees Celsius, and we don't know the final temperature. Okay. So we have a problem because we do have two variables for both of these, okay? So a key thing that we have to notice is that it does tell us that it is the same liquid. So liquid 1 and liquid 2 are the same. So they're going to have the same specific heat. And so what we'll find in the equation, and I'm just going to kind of cancel it out now, is that they're going to cancel each other out. Okay, and I'll kind of show you that in that. So they're going to have the same value. So whenever we kind of like multiply them all out and divide, they would actually cancel each other out. So we kind of can just ignore that. And then because these two liquids are allowed to come to the new temperature together, they're going to be equal. Okay, so whenever two substances are left to basically mix together and reach this new temperature, it's an equilibrium. So they're both going to be at equal temperatures. So my TFs are going to be the same value for both samples. Okay, the next step is I do need to figure out which one is going to be my absorbed and which one is releasing the energy. Okay, so if I have a liquid that's 35 degrees and I have a liquid that's 60 degrees and I put them together, I expect that the temperature that it's going to equal out to or come to equilibrium is going to be between 35 and 60. Okay, so liquid 1 is going to heat up. Okay, so it's going to actually absorb the energy, whereas liquid 2 is actually going to cool down. So it's releasing energy. So liquid 1 is going to be my absorb. Liquid 2 is going to be my release. Okay, so my mass for my absorbed liquid is 0.75 times my C times final minus the initial temperature, which was 35 degrees, is equal to negative mass of the second substance, so 0.25 C, and then my TF minus my initial, which is 60 degrees. Okay, like I said before, my C's are going to cancel, okay, because they're the same value because it's the same liquid, right? So I'm going to distribute this 0.75, so 0.75 TF minus 26.25 equals, and then I have negative 0.25 TF plus, because it's a negative times a negative, and then 15. So I did the 0.25 times the 60 to get 15. So I'm going to add the 26.25 to the other side and then add the negative 0.25 TF to the other side. So I'll get 1 TF, so just TF, is equal to 41.25 degrees Celsius, because this is our final temperature. For example number 4, a blacksmith heats a 535 gram piece of iron to 480 degrees Celsius until it glows red. The hot iron is added to a tub containing 24 liters of water at 18.5 degrees Celsius. If no thermal energy is lost to the surrounding, what is the final temperature of the iron and water after all thermal energy is transferred? So once it's reached equilibrium. Okay, so I have my iron and I have water as my two substances. So for iron, the mass, they gave it to us in grams, so I need to convert it to kilograms. So 0.535 kilograms. Okay, my specific heat, I have to go back and look at the chart and find iron. And I should find that this specific heat is 460 joules per kilogram degrees Celsius. and then my initial temperature is 480, and then we are trying to find the final temperature, okay? And we should recognize that the final temperature should be the same for both substances because we're trying to reach that equilibrium. Okay, for the water, they gave it to us in liters. Remember that 1 liter equals 1 kilogram, so 24 liters would equal 24 kilograms. Okay, the specific heat of water, again, I go back and look at that chart and find that it's 4,186 joules per kilogram degrees Celsius, and then my initial temperature was 18.5 degrees Celsius. Again, we're trying to find the final temperature. So we need to determine which one is absorbing energy and which one is releasing energy, okay? So we expect that it's going to be between the 480 and 18.5 degrees Celsius. It's going to be somewhere in the middle. So the water is actually going to be heating up. So this one is absorbing. And then the iron is going to be cooling down. So it's going to be releasing energy. So for my water, which is the absorbing one, I have a mass of 24 times the specific heat times my final minus the initial 18.5. It's equal to negative the mass of my iron, 0.535, times the specific heat, times my final temperature, minus my initial. Okay, so whenever I multiply, distribute, and then solve for TF, I should find that my TF is equal to 19.63 degrees Celsius. For your practice problems, they're all pretty straightforward. Nothing too tricky. The big thing is just making sure you know which one is being absorbed, or which one is absorbing energy, which one's releasing energy, keeping track the different variables. And you do not have to do question number 7.